then the 14 through 8, that gives us the June through December in the right order. Not going to spend too much time on how we map those, but that's going back from June, looking back 1 period, 2 periods, all the way back to 12, how you just reorder these so that you get this bar plot. Let's see, so if you want to see how this compares to seasonality in U.S. births over a longer period of time, you can click on this link. That's a fun little visualization. I'm not going to do that right now. I'm going to go ahead and look at some ways to decompose this time series visually into level, slope, and seasonality series. So this is a view of the data at the top. This is the seasonal components, so you see the peaks in, what did we say, August, and the troughs down here in, what did we say, February. We've also got the level, which is slightly declining, so we're up here at 360 some, and then we're getting down to 330 some. And we've got a trend that is very slightly decreasing, but of course changing over time. There's no change in the seasonal pattern. The gamma reflects that. And while this looks like this is changing and updating a lot, the scale is not reflective of a very big change over the time period. So this is what the beta goes with. Now the level is changing quite a bit over as we sweep through the data, and we can see that. Our initial estimate of the level was 365. It ends up at 325. And in the model, that's not surprising that it updated, because we've got a fair amount of weight that we put on most recent levels when updating our view of the level. Our alpha is not down near 0 in our exponential smoothing model. So now what we're going to do is we're going to go ahead and run a horse race with 4 models. And the way we're going to do that is we're going to set up a training set, and we're going to train our models, our 4 models, on a training set that goes from January 2007 up to June of 2011. And then we're going to see how the models do on the following year. So that will be the testing set. So these will be 2 new time series that we set up using this Windows function. Take the births time series, all 66 months. And take just a snapshot, just a portion of that overall time series from the beginning to somewhere in the middle, and that will be the training set, and then the testing set somewhere 1 month ahead of that, cut all the way to the end. So I'm going to run this, set up those time series. So here they are, training, testing, and then of course this is the full time series, just to check that we got the split right. Let you spend some more time with this. Now we're going to forecast going 12 months ahead using the time series, and our first model is going to be a naive prediction. And a naive prediction you can read about in the Practical Time Series forecasting book. It's in section 3.2, but it's basically just take the last data point in the time series. That would be this data point. I want to get the right one. It's this data point here. That's June 2011. Take that data point and use that as the forecast going forward 12 months. The seasonal naive is a bit like that, but it's go forward the 12 months and take the so let's see, let me be clear about this. So the naive forecast, when we want to make 1 step ahead, 2 step ahead, 3 step ahead, all the way up to 12 steps ahead, it's always this same forecast, 338,000. When we want to use the seasonal naive forecast and we want to go 1, 2, 3, up to 12 steps ahead, what we do is, when we want to make the 12 step ahead forecast, which is also a June, we're going to use 338. But when we want to make the 11 step ahead forecast, which is a May in 2012, we want to use this forecast. We want to use this May's, the 2011 May number, 327,000, as our May 2012 forecast. So this will allow us to use something that's naive to look backward to the most recent value, but make sure that it's seasonally adjusted. Okay, so that'll be the first two models. Those are very simple models, but sometimes they can be quite difficult to beat. Okay, so here's our third model. We're just going to let the ETS model go and fit its very best model. And now we're making predictions with it as well in the same block. And here is a time series linear model. And this is like a regression model where we have put in a trend variable and we've put in a seasonal variable, or set of variables. What this is, this trend is just 1, 2, 3, 4, and so on. It's just an index of months going forward in time. And the seasonal variables are a set of dummy variables, one for each season, or one for each month here. And so that would be a dummy variable for January, then February, then March, and so on. So actually, let's go ahead and run this model. And I want to put in, let's see, we have the summary here. So we're going to plot the, I'll just jump forward before we see which of these models does the best. I want to just show what this linear model does. This is the regression output in R, and there's an intercept which is 356. There's a trend which wasn't far off the trend we saw above, which was -5. What was that? I want to get that up here. This was -557 from the additive additive trend, additive seasonality model. What we're getting from a linear regression model isn't all that different because this is a global model as well. This is essentially like setting alpha, beta, and gamma all to 0. And then what we're seeing here is our seasonal factors. And it's dropped one of our dummies as it should. So this is our February, our March, and so on up to our December. Let's see, so we can see our peak our peak is in August and our trough is in February. So that's that linear model. And then what's interesting about the ETS automatically fit model is that because we trained on less than all 66 points, we trained on 54 of those points, that's the size of our training set, we've got a slightly different model that was optimally selected. We selected the multiplicative error, additive trend, and multiplicative seasonality. So not the same model we got up above when we fit all 66 data points. And so we've got multiplicative seasonality. So rather than seeing additions and subtractions of births as we roll through the seasons, we have multiplicative factors. So we take, this is like taking 0.8% above for thinking about I want to say this is, got to be careful, that's a December. And so a November is 95% of the level, and so on. And so our greatest month here is, I'm assuming that this is December, November, October, September, and here's an August, which is 106 or 6% higher than our level plus trend center line, if you will, or mean. Okay, so now I want to go up and I want to run this accuracy function, and so now what we're going to do is we're going to take these models' predictions, and this accuracy function is a function inside, so let's give ourselves a cell here, and we're going to use our question mark, which is our help function, if you will, and we're going to see what the accuracy function does. So the accuracy function takes a forecast object, and then the next object it takes is the vector containing the actual values of the time series. So we've got forecasts, and then we've got the actual values, and it will give us back how accurate our model is. Actually, several scores for accuracy. So our 4 models are going to be run in terms of their accuracies, and we've got some errors here because I didn't run these 2 lines. Need to do that. I'm going to run the naive and the seasonal naive models, and then I'm going to rerun this model by just putting my cursor in the cell and pressing the play button, and now I've got some nice tables that tell me, okay, so this is the root mean squared error, this is the mean absolute error, this is the mean absolute percentage error. And if you, for instance, focused on mean absolute percentage error, what we find is that this seasonal naive does pretty well, and it almost beats our linear model. Our linear model does best here. Now, if you used a different performance metric, you see that it's actually here on root mean squared error. We're comparing the 17,000 for the seasonal naive. Here, let me see if I can. So this is the seasonal naive. This first report goes with model 1. That's a high root mean squared error. This is quite a low root mean squared error for the seasonal naive model, 6757, and that's beating the ETS model and our regression model with a trend in seasonal dummies. And so here's a demonstration that it can be quite difficult to beat these naive models. And we've already looked at the readout on this. And so if we want to go ahead and take a look at a plot of these models, you can see this was just the naive. It's the same level for all 12 of the months out. This one is just look back to the same previous month. Most recent month, that's the seasonal naive. This model does pretty well on root mean squared error. Here's the ETS model. You can see this one's getting pretty close in places, and the linear regression model is also looking pretty good. Okay, so I will let you go ahead and explore a similar type of analysis with the census data, and you can run much of this analysis and choose a best model that would help you forecast census and denials for 17 months ahead. So that's it for this video. Thank you.